We're going to introduce an early idea of optimization, and it's going to be a little hand-wavy. But the idea being, up till now, you've been given a truss. It is one truss. You analyze it, and you find the member forces under a certain load. The next thing you're going to want to do, though, is change the design and see what happens. So that's what we're going to look at next. We're going to explore how we can change the design as part of our code and work through the consequences of it. I need this in a second. So let's take a look at that. It's easier to work with angles and this kind of idea. So what we're going to do here is explore what happens if we change this angle here. So we're going to talk about a really flat thing, or maybe higher, or super high like that, just to see what changes there are or changes are required in the mathematics and in the code. So we're going to start with W23, which is on the course website. And W23 is exactly what we had as the output from our Monday class, where we looked at, or Tuesday class actually, sorry, Tuesday, 2 classes ago, that's what I mean, where we looked at that same truss, and we had 30-degree angles and 60-degree angles, so that's the original truss that we had there. And we went through the force calculations. We built the A matrix, which is the coefficients of all the unknown forces, the B vector, which was the external forces, all organized nicely, and we had our force at the end. And what we're going to do is tweak this now. If we look back at our diagram, there's only one 30-degree angle in this, which makes life a little bit easier. What we're going to do is change that 30 degree to be maybe 5, maybe 10, maybe 15, and as soon as we start doing that, I'm hoping your minds are going to, hey, I'm going to loop over those angles. I'm going to try 5, try 10, try 15, and see what I get. So we're going to change our angle and make it a variable instead of hardwiring it to be 30 degrees. So here we go. We have 30 degrees here and 30 degrees here. We're going to call that now alpha, but you can't type in alpha, so we'll just call this SA and CA. Those are the 2 components that were used in the 30 degrees. And we see it in a few different places here in the actual matrix. So we have to change it in both places, where we create it and where we use it. And so I think there's 6 locations, yeah, all in the first 2 columns. We don't change the signs, we just change those values. Why do we change the name? Because if we call it S30 but the angle is 20 degrees, that would be a bit weird. So now we're making a little closer relation between what's written and what it actually means. So those first 2 columns, we're going to change all of those to sine alpha, cos alpha, and then we're going to add a loop. All right. So what we're going to do is put a loop in here and say for A is equal to, we're going to start at 5 degrees, go up by 5 degrees, up to 85. If we go to 0 or 90, weird things are going to happen. And that's how we do a loop in MATLAB. And they're going to put an end at the very end of this. Okay. Let me just make that all visible at once for a second. There we go. And let's shrink that, just get more space. So that's our entire code block there. Now, because as soon as we have a loop, we should be indenting things differently. What would be a nice thing to make this look prettier? What 2 keystrokes on a PC, and I think similar ones on a Mac, will make this look nice? Yeah? Control I and Control A to select everything first. Control A and then Control I. And now we can see what's inside the loop, everything that's indented, and what's outside the loop. Okay. So what is this going to do? Well, in principle, what we want to do is set an alpha, build the A matrix, build the B vector, and then find the force balance solution, which is what are the beam forces as we change F there. Any difficulties people see so far? You think we're good to go? Yes? Absolutely. I'm glad you caught that. So if you take a look up, be careful what's inside and outside your loop. I'm going to run this once just so we see what happens when you don't get this quite right. And function F5. We actually get an error right off the bat. Undefined function or variable A. And you can click on the link here. It's actually quite nice. MATLAB jumps you to where the problem was. If you click on there, it says, hey, this line here, A was not defined. And It is absolutely correct, because the loop that defined A was about 8 lines down. So wait, I can't find the sign of an angle that I haven't defined yet. I want the angle to change. So you have to think a bit carefully about what's inside and what's outside the loop. These 2 lines depend on A, and if A is changing, they better be inside the loop. And again, Control A, Control I to re-indent. There we go. The other ones do not have to be inside. Why? Because they're just sine of 60. Whether that happens inside a loop, outside a loop, it's still sine of 60, cos of 60. But that is going to fix the problem you mentioned. Perfect. So now we should be able to run it and have it do something a little more sensible. W23. Fantastic. I get a whole whack load of output, a whole bunch of Fs. Stacks and stacks of Fs, in fact. There we go. There's the first one. So what is this doing? What is this doing? What's the first F correspond to? How should I interpret those numbers? Sorry, actually, let me pause and see if there's any running problems. Anyone having difficulty or encountering other errors than the one we demonstrated there that are easy to describe? Okay. Okay. So interpretation. This is the single biggest thing when you've got these programs running, especially as you get more complicated programs, to go, what the heck does this output mean? What does this output mean? Anyone care to put it into words? Crickets. I'm hearing crickets. Yeah. Perfect. Force in each beam. This is 10 numbers, and there are 10 beams, and it's for each angle. So this corresponded to the angle that was the first loop, which was 5 degrees. So what this is crying out for is better output, because right now we can't really tell what the heck is going on here. So what I'd be tempted to do is not use the default printing here, but actually make a nice print statement. Say what the angle is. It's a nice decimal thing or integer. Degrees. Oh, thank you. F print and F. Thank you. And we put A at the end here. So this is the fprintf command we covered last class. So show the angle is equal to some number, finish the quote, put the /n, which means new line, and then we put the A at the end so it'll fill in that integer. And if we do that and run it, I'll do a CLC, clear the screen here, run it again, and okay. Now we get the angles at least, but it makes sense to put a print statement after that that prints the actual forces. And here it's a long vector, so I'm tempted to just do it in 2 stages here. And we'll just print %.0f/n f. We'll try this out. There we go. That still looks hideous. All right, I'm going to do one extra tweak here. That's looking better. Okay. So let me show you the sample of the output and where it comes from. There we go. So we got the print statement for the angle. So the angle comes out first. Then we say just print the word forces, because we don't want to worry about it too much. And then the next print statement, the 8.0f, means save myself 8 digits. Don't show anything after the decimal. I don't care about 0.1 newtons in a truss. That's a little too small for me to care about. But the 8 says at least reserve 8 digits, and that lines things up, is what that does for you. And then print f. So f has 7 or 10 has 10 numbers in this case. It'll print them all out using that formatting, and it kind of looks like what we'd expect. Beam 1 through whatever. 1 through 10, here are the forces. Beam 1 through 10, here are the forces. Beam 1 through 10, there are the forces. All right. Pause for any technical issues or questions about that syntax or the logic behind it. Yeah? Sorry, argument dimensions are not consistent?
Yeah.
That's okay.
CAT arguments.
Line 32, yeah. So it actually tells you the line 32 there. If you click on that, it'll take you there. So if you click on the error message, it'll take you to the line where the problem is. And there, oh, your SA and SA are joined. There's no space between them. Okay. So you have to be careful editing your A matrix. Any other issues, running problems, or understanding the syntax? There's some discussion. Go ahead. Yeah. What does the \n mean? The \n means go to the next line. If we didn't have that, we'd just get all our forces on one line, which actually, now that I think about it, might not be such a bad idea either. We can take it out of this line with the forces. We can clear the screen and run it again, and this might be actually, well, not a lot easier to read. It changes the output, but we don't have a new line between each of the forces. It's a little more compact, though. The downside is our angle thing gets stuck on the end of the last line before it. At least we can see them all at once here. Excellent. Any other interpretation or code questions? Okay. All right. So what I do want to feature here, actually, this is actually not a bad way to show it, because it shows that a lot of things stay the same, and then some things change. So let's go up to the top here. The forces on most of the beams, like these ones down here, stay the same. So what we're changing here is the angle, and changing that angle doesn't seem to affect how these beams are loaded up. It does seem to change how the ones at the front end, F1 through F4 here, do get changed. Sorry, question though.
I just have a question about the last print statement where you put percent 8.0f.
Yep. Good question. So I put this percent 8.0f, and the question is, if we just want an integer, can we just print an integer? We can try. I think what's going to happen is it's going to look like hell because it's not actually an integer. It doesn't make it an integer. It says, I think it's an integer, and try to print it that way. If we tried, I think we're going to get that. So I would say no, we probably don't want neither. But honestly, the one message I would say through all of this is there's nothing you can do to break MATLAB. You might have to reset it. You might have to turn your computer on and off again. But that's the worst sort of restart you might have to do. So if you're wondering, hey, I wonder if that'll work better, try it. Just know that Control-Z undoes your changes, and go back if it doesn't work. But do not have any fear at all about experimenting. This does not cost anything except a little bit of time. All right, clear the window. There we go. OK, so we're going to add a little bit more refinement here, because part of the job of any computer program is to distill, is to not throw tons and tons of data at the user, you in this case, if a lot of stuff isn't changing and then I'm not that interested in it. Okay? What I might be interested in to start with is which beam is the most heavily loaded. So especially off the top there, when the angle was 5 degrees, what we got was a huge force, huge resultant force from pushing down the top. And the things are at such a shallow angle, to get the vertical component that we need, we have to actually have a huge compressive force in those first two beams. As the angle gets steeper, we need less force because you've got more vertical component to the angle, to the force there. So we see a nice drop-off in the force distribution. And so what we'd like to do is maybe capture that somehow, like in a print statement, and see how that works. One of the things that you might want to do is tease out the maximum value. So instead of printing all the forces all the time, let's just print the maximum force. So display only the maximum force. OK. So there's ways you could do this with for loops. But this is MATLAB. This is something people use all the time. And finding the biggest number in a set is probably something people want to do a lot of the time. So it's probably built in. What might be a good name for a function that finds the max of a vector? We can short it there. How many people have heard of this function already? Yes. Go ahead. You forgot? OK, you cannot forget this. What's it called together? Max. Yeah. OK. Exactly what you'd expect. So if we say fprintf, and we can say the max force equals percent 0.0f. Let's say get the 8 there. And max of f. That's going to work nicely. Actually, let's do this in two pieces. Let's say max f equals the max of f. And we'll get rid of the brackets here. OK. There we go. Nice. All right. So that distilled the output quite substantially. Now we've got the largest possible values. Wait, some of them were like 86,000 though. What? Why am I not seeing the 86,000s? Because those were bigger. There's a very good reason. This is part of the job. Why am I not seeing the 86? Yeah. It's outside of the loop. Actually, no. They're in the F. Everything's inside the loop. Let me go back to the last one, show you the comparison. I'll comment that line out and bring this one back and do it again. So there's the 86 right there, but I'm getting this guy instead. Yes, it's negative, exactly. If you say what's bigger, 76 or minus 86, well, MATLAB says minus 86, or sorry, it says 76. We wanted to give the maximum, though, in magnitude. How would we go about doing that? Absolute, yeah. Absolute value, again, something built into MATLAB. You can search for it, you can Google it, or we can recognize that we want to take the absolute value of what we're doing here before we take the max. All right. And this will tell us the positive version when we're done, but that's okay. So let's, again, there's Control-R, Control-T in the PC world for commenting lines out. Let's try that again. There we go. So the biggest force in absolute value is 86, then 43, then so on. All right. Now there's one last little piece that I think we should add here, which is we have lost some information by not showing all the forces. And the biggest thing we've lost is which beam has this largest force that we just found. So here, again, finding the largest value is something that most people want to do. Another very common thing people want to do is say, find the largest value. Oh, it's the fifth thing. I would like to know that it is the fifth thing. So this is something you can take a look up in MATLAB as well. Presumably it's related to the max function. So we're going to look up, we're going to highlight it and then press F1 here. And it's going to tell us some stuff. All right. So this is what we did. We did the first one. We said, I want to find the maximum number in an array. Good, did it. However, we might want to do something else. We might want to know where the biggest one was. So if you look at the various ways we can use the function, there's one that gives me two things back, the third line down there. That one sounds interesting because it might tell me where and what the maximum was. And if you scroll down further, this is how you use it, and then here's what it actually does. Finds the indices. That's what we want. Find out which index. Index 1, 2, 3, so beam 1, 2, 3. Which index has the maximum values and returns them in a vector I. All right. So what we're going to do is change our syntax a little bit to have two outputs instead of one. So this is a little special for MATLAB. And index. So we don't change the call. We just say I'm going to get two things back, the maximum and the index. And we'll see how this works in beam I. So a few changes to those last two lines there. Notice a couple of technical details. Square brackets, we can't just say maxf comma something. It has to be packaged together as a vector. So maxf and index and square brackets, those are going to be my answers. And I added a %i for an integer, because I'm going to be saying, is it the fourth beam, the fifth beam? What beam is it? That's an integer. And I put another thing to print, which is the index at the end there. With those two changes, and my fingers crossed, this should hopefully give us what we want. Fantastic. Beautiful. So we've expanded the detail in our output now. Beam 1 is under the biggest load. Beam 1's under the biggest load, but the load is going down until after a while, we flicker over to beam 4, 7, 4, 4, 4, and so on. Now, actually, beam 4 and beam 7 look like they actually had the same load in them. Does that make sense? Well, let's take a look back at the picture for 1 second. Our truss looked like this. Here's beam 4. Here's beam 7. They're actually going to have the same, essentially the same force in them. But MATLAB, with its solving, as we saw with last class, might round things a little bit, like 10 to the minus 16 Newton difference. It's going to pick by a hair's breadth which one is bigger. Because of symmetry, we know one of the two is, but we'd have to infer that. We'd have to add that ourselves. MATLAB's not going to tell that to us. But it makes sense. In the first rounds, it's the, let me clean this up here. When it's shallow, the biggest forces are in these beams at the top. But when we get up to the really vertical things here, it doesn't take much force to resist the vertical part there. At that point, F4 and F7, beam 4 and beam 7 end up having a larger magnitude of load in them. All right, back to the code for 1 second. Code. There we go. Code. Any issues running it or sort of understanding what those modifications to the max and the fprintf do. Yes, please. You're getting a max force in beam 1 for every line. Does the force change, or is it always the same? That sounds more subtle. Okay, I'm happy to take a look at that afterwards, but I think it'll have to be afterwards. So I can't think of an obvious reason why that would happen. The usual reason would be something's inside the loop when it shouldn't be, or maybe you used a different name in that second thing, index and index. That would be the other thing that might be different, but I have to double check. Any other issues running this or interpreting this? Yeah? The force is the same. Okay, if the force is the same, most likely the angle hasn't changed. That's typically because the angle wasn't put inside the loop. The angle change wasn't put inside the loop. If nothing changes at all in all your output, that usually means that something that should be changing every time you loop through is outside and not actually changing the way you think it is. That's my first guess anyway. Other technical issues? Okay. Okay. Then let me just pause here to make a wrap-up statement before we move on to our next application. This kind of, this is almost what I want, but I need to tweak it a bit, is going to be what you see throughout the course. This is going to be a common theme.